Alright, so let's talk about timing now. So we've got a basic handle on clocking in this PIC processor in particular, with the built-in, straight out of the box, no modification. The internal oscillator is around 31 kilohertz, which means it will execute approximately 8,000 instructions in 1 second. Well, we can use this to generate delay loops. So what's a typical delay loop? Well, you can find one in Lab 3. So let's take a look at Lab 3. So Lab 3 has a little bit of a synopsis of all of this. Need to use a delay function, okay? And the code down here, which we're about to play with, shows you an example of making a delay loop, okay? And it's based on the following assumptions. The internal oscillator, it's called the RC, resistor capacitor clock, is 32 microseconds, okay? That's about 31 kilohertz. So an instruction cycle is 4 of those clock ticks, which is 128 microseconds. Okay, so we're going to do a lot of these kinds of maths in the coming weeks. So 8,000 instructions per second. That's approximately 125 microseconds per instruction. Okay, if it was 1,000 instructions, that would be 1,000 microseconds. If it was 2,000 instructions, that would be 500 microseconds. Okay, these things go as reciprocals. And probably one of the most challenging / annoying parts of dealing with this aspect of the processor is keeping straight all of these when you divide, when you multiply, when you put this on top or bottom. And I don't have a good trick for that, except to go back to simple units, right? So 1,000 instructions per second means in 1 second you get 1,000 instructions, which means in 0.001 seconds you get 1 instruction. So that's 1 millisecond, which is 1,000 microseconds per instruction. And then if you increase the clock speed, 2,000 instructions per second, then you decrease the time it takes to execute an instruction. So this is 500 microseconds per instruction. 4,250, 8,125 microseconds. So this is our baseline. Or, you can just look at the beginning of Lab 3 and pull these numbers out. Okay, but it's nice to know where they come from. So T oscillator, that's the internal clock, that's the oscillator frequency, that's the 31 kilohertz. Okay, the instruction cycle, that's the time it takes to do 1 instruction, and that's about 128 microseconds. 125, 128, depends how you cut it. Alright, so if we write code that takes 128 microseconds, If we write code that consists of a single instruction, it's going to take 128 microseconds. If we wrote a program that had 8,000 instructions, how long would that program take to execute? It would take about 1 second. If we wrote a program that consisted of 800 instructions, that would take about 1/10 of a second. So how do we write a program that takes 800 instructions to execute? Well, one option is to write 800 no-op statements. That's not a really great option. Okay, that's going to chew up most of our available program memory. But remember, we can make loops. So what if we did a no-op and we jump back to the beginning of this and we put this in a loop? Well, if we made this an infinite loop, it would never come out of it. It would be an infinite delay. But if we could make this so that it took 800 loops before it came out of this, right? We could execute 800 no-op instructions. That would be a nice 1/10 of a second delay. Except that this branch also takes time. And counting from 800 down to 0 also takes time. So here's our quintessential delay loop. Load something into the W register, decrement the W register, and if it's not 0, come back up here. And if we figure out how long this takes, and we know what the initial value in the W register is, we can figure out how long this whole chunk of code takes, and we can build a timing loop. Okay, so this is done for you in this sample code. So usual initialization, addcon 1, trisb bit 0 is an output. We're going to use that to demonstrate what's happening. But here's the real heart of this program. It's this delay loop. So it's a label called delay. And the idea is when you call this, you should have first placed a value into this file register called dcount, okay, which is just stored at location 80. And whatever value you put into dcount, this loop will wait that many tenths of a second. So if I put a 10 into dcount and I call delay, I should return from here after 10 tenths of a second, 1 second. If I put a 1 into dcount and I call delay, I should return from here after 1/10 of a second. So this is a general purpose function we can use to create a delay anywhere from 1/10 of a second up to about 25.5 seconds. And to use it, load a value into dcount, that's the number of tenths you want to wait, call delay. And when you return, you'll have seen that much time has passed. Alright, so what does this delay do? It puts the number 195 decimal into the W register. And then it says decrement the W register, do nothing, and then if the result of that decrement was not 0, go back up here again. So how long do these 4 instructions take to execute? Typically 1 cycle for the decrement, 1 cycle for the no-op, 2 cycles for the conditional branch. The exception is if we don't take this branch, remember from our data sheet, that last branch may take only 1 cycle. But we don't care about that. That's just fine detail. Most of the time, right, in fact 194 times we're going to take this branch because decrementing WReg won't have reached 0. So most of the time this is going to be 1 cycle, 1 cycle, 2 cycles. That's 4 cycles to do this loop. And we're going to do this loop 195 times. So 195 times 4, that's how many instruction cycles we're going to consume. And if it takes 128 microseconds per instruction cycle, this whole loop, right, from the decrement, the no-op, and the branch of not 0 is going to take about 100,000 microseconds. That's 1/10 of a second. Right, a second is 1,000,000 microseconds, 100,000 is 1/10 of that. So this is a 1/10 of a second delay loop. And we wrap that loop inside a bigger loop, which assumes that we've loaded a value into this dcount. And this bigger loop, which starts at delay and goes down to here, basically says, wait 1/10 of a second, decrement dcount. If it's not 0, go back up. Wait another 1/10 of a second, decrement dcount. If it's not 0, go back up. So this outer loop will be executed dcount times. So we have an outer loop which executes dcount times. and we have an inner loop which takes 1/10 of a second. So this is sitting here and it keeps looping back, and this outer loop keeps jumping up, and so from here to here takes decount over 10 seconds. And then at the end, after decrementing decount reaches 0, we execute a return. Alright, so what does this program do? It does some setup. It sets up tris B, bit 0 to be an output. And here's our main program. First thing we do is we toggle bit 0 of port B. And then we put a 20 into decount and we say delay. Wait 20/10 of a second. That's 2 seconds. And then branch back up to the top of the loop. That's the whole program. So what should this do? It should toggle bit 0 of port B every 2 seconds. Should go high for 2 seconds and then go low for 2 seconds and just keeps going back and forth. And if you code this up and you dump it into a PIC18F1220 on a breadboard and you hook up an LED to the pin corresponding to RB0 and you power it up, you'll see that LED blink every 2 seconds. It'll turn on, then it'll turn off. And this is very common, especially on smaller processors. This is a really common way to introduce timing delays. There are more sophisticated ways, and we'll be talking about those next week. But quick first order, if you want something to take approximately 2 seconds, this is a pretty good way to do it. If you sit there and you look at this, you're going to say, yeah, that took about 2 seconds. Right? And if you're not worried about pinpoint precision, this is plenty good. So let's code this up. Really fast typing. Alright, so here's the code. And let's build that, and let's run it. And let's start stepping through. So we're going to call our delay function. And delay is going to put 195 into the W register. Okay, so I can see up here on the upper right, W register is C3. That's the hex value. I'm going to decrement, and if it's not 0, I'm going to go back to the top. So W is C3. Let me zoom in a little here. I'm looking at W right here. Decrement it to C2, it's not 0. Decrement it to C1, it's not 0. I'm going to do this 195 times. Well, I'm not really going to do this 195 times. But if I did this 195 times, right, I would keep running through this loop over and over and over. And if I look at file register 80, let me throw some watches in here. Alright, file register 80 was initialized to 14 hex, that's 20. And as I go through here, W register is going to slowly decrease. Well, let's cheat. Let's just go in here and hardwire a value. Let's suppose we count it down all the way to 5. And we count down to 4 and 3 and 2. And we decrement it to 1. Alright, so we just decremented it to 0. We did a no-op. This would say if it's not 0, go back to enter delay. Instead, we're going to come out of that inner loop, and now we're going to decrement decount. Decount is 14 hex right now. That's 20 down there at the bottom of the screen. And we decrement that, it's going to go to 13. And if that's not 0, which it isn't, we're going to go back up to the top of the delay, reinitialize W to 195 decimal, and count for another 1/10 of a second. Okay, that's how we generate delays. Now, if you have been playing with this extra tool, that I mentioned a while ago, this graphical simulator, we can get some essence of this. The simulator is not quite running at the same speed as a 31 kilohertz PIC processor. It depends on your CPU that you're running this on. For me, this is running at about a 16 kilohertz clock rate as opposed to 32. So my LED is blinking every roughly 3 to 4 seconds instead of 2 seconds. But you can still see that, you know, there's clearly a timing factor in there, and it's blinking accordingly. And if I were to change this code and say, well, let's wait 0.5 of a second. Let's go ahead and build that up. So this should blink every 1 second on my simulator. So I can load that file in. Alright, well now it's blinking at a faster frequency, about every second. So you can get some essence of the behavior of your code using this tool, okay? But again, it's really not a debugging tool. It's really kind of taking the place of suppose I were to plug this into a proto board, load the code in, hook up some LEDs and switches, what would happen, right? And this will give you an approximation of that. But if you want to do more precise timing, we can actually look at a stopwatch. So if I go under Files, Simulator, nope. Somewhere under here. Nope. Window, debugging, stopwatch. And where did it go? Let me stop this. So let me put this back to our original code. And let me rebuild that. And okay, so I have a stopwatch window up here. So normally when you do window debug stopwatch, right, it pops up down here. I'm just going to drag this out and put it up here so I can look at my stopwatch window while I'm also looking at my variables down here. And I'm going to hit my garbage can to clear out my screen. Okay, here's what the stopwatch does. It basically tells you how much time has passed from your last breakpoint to your next breakpoint. So I'm going to set a breakpoint up here at the top where this bit toggle is. And I'm going to go ahead and run this. And it's going to tell me 5 microseconds have passed since the program started. Okay, and I'm going to run this, I'm going to say continue, and it should, you know, toggle port B. And let's put port B on here just for fun. Okay, so port B is a 0. It's going to toggle port B, it's going to call this delay loop, and then it's going to come back up here and hit another breakpoint. So if I run that, 2 things will happen. One, port B's least significant bit will toggle, that's RB0, and it tells me that 15.668 milliseconds have passed. And if I tell it to continue, it'll say 15.668 milliseconds have passed, and port B changed to a 0 on that least significant bit. So I can see that my least significant bit of port B is toggling, going from a 1 to a 0 to a 1 to a 0. And I can see that it's taking about 15.7 milliseconds to go through this whole loop. Okay, so here's what you got to know about doing debugging on MPLAB. The simulator is assuming that your chip is not being clocked at 31 kilohertz, but rather at 1 megahertz. Actually 4, but divided down. So MPLAB, I'm not sure why people are cutting out of here, because the class goes till 4. But anyway, so MPLAB assumes 1 million instructions per second versus 8,000 on the physical hardware. And there's ways you're supposed to be able to change MPLAB's configuration to say I want you to run at 8,000 instructions per second. They don't seem to work. Okay, so we're stuck with this 1 million instructions per second for MPLAB. But we can do exactly the same calculations that we did a moment ago in trying to figure out how long this program is going to take to execute. So let's look at the lab again, right? We're doing 195 iterations. It takes 4 instructions per iteration. So that's 195 times 4. That's, let's go ahead and be precise. I will not embarrass myself. I'll use a calculator. All right, so that's 780 instructions. And we're executing this loop 20 times. So that's 15,600 instructions inside this delay loop. And if it executes 1 million instructions per second, that's how much time it takes to execute this delay loop. And if we multiply by 1,000, that's how many milliseconds it takes. So running at a 1 megahertz instruction cycle, this delay loop should take 15.6 milliseconds. That's exactly what it's taking. Well, 15.668. Because there's some extra stuff. There's stuff in the beginning and there's stuff at the end. Right, so it takes slightly longer. So and I multiply by 20 because the code is saying put a 20 into decount, so this delay loop will execute a total of 20 times. Right, remember delay waits this many this much time n times, where n is the value inside decount. All right, so when you're working on your code for lab 3, right, you can use the stopwatch function and set breakpoints at the places that should be 2 seconds apart. But when you do this in MPLAB, you're going to see that they're actually 15.668 milliseconds apart, or something along that line. Okay. On the other hand, if you go ahead and you load this into that GUI tool, you should see something approximately with the same timing that you're getting with, depending on your CPU speed. If CPU is faster than mine or slower than mine, it'll be more or less. But it should be somewhere in the ballpark. Okay, and you can actually tweak the timing a little bit in your program if you want a 2-second delay. And when you run it on the GUI on your machine, it takes 10 seconds. Right, you can cut your time in by 5, and that'll bring the time down to 2 seconds. So you definitely want to make use of functions. You definitely want, in particular, your delay routine to be a separate thing that you can call and return from. Okay, and then you can tweak the timing in here if you want to use this in MPLAB, if you want to use it with the GUI, if you want to use it on a piece of hardware, if you want to change the amount of time it takes, right? You can just play around with the values in here and not have to change your main program. Okay. The other thing to remember with calls is that everything is global. Okay. In higher level languages like C programming and stuff, we say don't use global variables. Globals are evil, and so on. Everything is global, right? Memory is memory. And so if I change a file register down here in this function, when I say return, that file register is still going to be changed. And if I use the W register inside here and I say call delay, when I come back from that call, the W register is going to be changed. So if I have a value that I care about, I better not just save it in the W register before I call delay. I better put it somewhere that this function is not going to mess with, and then read it back out of there. Okay, so you'll see all of this when you're working with this in MPLAB. So let's talk about the lab, right? What's the lab? It's your favorite 3-way traffic light controller. You've never seen this before, right? 3-way intersection, west, south, east, 1 lane each, 3 lights, red, yellow, and green, and a car sensor telling if there's a car present on the west, south, or east, East gets priority, south gets next priority, west is lowest priority. Alright, and you're going to write a program to control these traffic lights. And the way your program should work is that if there is a transition from green to red, it should take 2 seconds, and during that 2 seconds, whoever had a green light should turn yellow, and then after that, it can turn red, and whoever gets precedence should turn green. It says 2 to 4 seconds, but 2 seconds is easier to watch, but it doesn't have to be pinpoint. Alright, so here's how we're going to interface with this system. We're going to use 9 pins. RB0, 1, and 2 will be the green, yellow, and red light on the west. That's these. And 1 will mean the light should be on, 0 means it will be off. RB3, 4, 5 will be the lights for the south. RB6, RB7, and RA7 will be the green, yellow, and red lights respectively for the east. We don't have an RB8, we've only got 8 bits coming out of port B, so we'll use 1 bit from port A for the red light. Okay, so pay attention to that when you're coding it up. And then the car sensors will come in on RA0, 1, and 2. And those are the sensors for the west, south, and east respectively. So all of port B is going to be an output. Make tris B a bunch of zeros. RA7 is going to be an output. Make that bit of tris A a 0. RA0, 1, and 2 will be inputs. Make those bits of tris A 1. Set all of your ADCON 1 to 7F, and you should be done with all the setup. And now make yourself a loop, right? And continually look at the car sensors. Right, so look at the car sensors, and if there's a car on the east, give it a green light. If there's no one on the east but there's one on the south, give that a green light. If there's no one in the east or south but there's one on the west, give that a green light. If there's no cars anywhere, your code should have made a decision about who's going to get the light. Maybe it'll be west, maybe it'll be east. Maybe you'll be mean and make everybody red, I don't know. But decide what you're going to do, okay? But now the trick comes when a car arrives, and you need to know what state the system's in. So if the eastern light is green and a car arrives on the east, you don't have to do anything, because the light's already green. But if the eastern light is green and a car arrives on the south, don't just make this red and green, right? You need to change the eastern light to be yellow. You need to wait for 2 seconds, and then change the eastern light to red, change the southern one to green.
But don't traffic lights go on a set loop?
No, these don't. Well, you could do that. I mean, if there's no cars present, you could slowly change from one light to another every 20 seconds or something if you want, but you're not required to do that. The only requirement is that you give a green light to whichever car has precedence, and you make your transitions from green to red go through a 2-second yellow. And if there's no cars, you can decide how you want to set the lights. So the code's not that bad, right? Basically, you're just going to monitor the cars, right? Monitor your inputs and look for a change in your inputs. If the inputs haven't changed, you don't have to do anything. If the inputs change, meaning that somebody else is going to get precedence, right? Then, jump down to a section of code where you change the green light to yellow, wait 2 seconds, change the yellow light to red, change the red light to green, and you're done. Go back to waiting for a change. Cars on the east always get precedence. This is the same as the 250 traffic intersections. So if there's a car on the east, you're going to make that light green, possibly after 2 seconds of delay. If there's no car on the east but there's one on the south, car on the south gets a green light. If there's a car on the west, nothing south or east, then west gets a green light. And so to test this, set up stimuli for those 3 bits that correspond to your sensors. And I would say set up the stimuli so you can make them low or high, right? So you can change those. And set up a stopwatch. put a breakpoint maybe at the top of the loop, or somewhere, you know, to indicate where your delay has started and ended. And when you change your stimuli to represent a car arriving or leaving, right, your code should go ahead and adjust the lights accordingly and hit breakpoints in your code to correspond to those changes, and look at the stopwatch to see how much time has passed. And then that would be, you know, part of what you would want to turn in under your observations and your discussion of your results, right? Basically, that's how you're going to test it to show that this works. And then throw it in the GUI tool if you want and play with it there, because that's probably a little more satisfying to look at for yourself. All right, so that's it. One experiment. Write some pseudocode for this one, right? Don't just leave me with, you know, 200 lines of assembly code to try to reverse engineer. Write up a high-level description of how this is going to work, either a flowchart or some pseudocode or something that looks like C, right? But something that captures the algorithm. And the algorithm is pretty small, but you gotta pin down what that's supposed to be, right? What's the behavior of this code supposed to be at a high level? And then go ahead and code it into assembly language and test it out. Alright, so state the problem in your own words. That's an introduction. Pseudocode, disassembly code after you've got this thing working. A test plan that describes how you're going to see whether or not your code works correctly, and then copies of your simulator output showing where you're stimulating the car sensors, and the corresponding results to convince me that your code's actually doing a traffic light control. And the usual boilerplate stuff at the end. Alright, other questions about that? You can use this code verbatim for a delay loop, right? But I strongly recommend making sure you understand what's going on in here. And if you don't, playing with it, right? Make some changes, mess around with it, see how that changes the behavior of the code. But you don't have to rewrite this from scratch yourself. You can use this verbatim. This is unrelated to what we're doing though, right? You don't want to toggle a light every 2 seconds. That's just an example of using this. And you got to figure out your own tris A, tris B setups and so on. Alright, I will be on Zoom in my online office until 4 o'clock. Let me know if you have any questions. Otherwise, go ahead and keep coding and have fun with this, and I will talk to you next time.